To see if it goes farther than Brittany's throw apparently from the last problem, Lulu throws a ball 20 meters per second, same speed, from a height of 1.50 meters, same initial height, at an angle of 30 degrees up from the horizontal. How far will it travel horizontally before it hits the ground? Ignore air resistance. So this is very similar to the last problem, but now rather than throwing the ball horizontally, it's being thrown upwards at an angle. So let's see what kind of effect that has. Well, we've read the problem. Let's draw the diagram. Here we go. Here's Lulu throwing the ball, but now the ball is being thrown at an angle of 30 degrees up from the horizontal. Again, at a speed of 20 meters per second and an initial height of 1.50 meters. Well, why don't we keep the same origin as we had last time? We'll just define the origin down here, x and y, on the ground, right below the initial position of the ball. What's the motion going to look like now? Just qualitatively, what's it going to do? Well, last time it was thrown horizontally and it just went down to the ground. Now, being thrown upward, the ball is going to start out going upward and then come down. Something like that. Okay? So now the ball is going to come over here before it hits the ground. How far does it go? Once again, we're looking for that distance to solve the problem. Well, we've put in our coordinate system. Next, what are the variables? Hopefully, maybe you remember them. X naught x, V naught x, Vx, Ax, Y naught y, V naught y, Vy, Ay, and T. And what do we know? What values do we know? Well, x naught, again, is 0. Y naught, the initial height, again, 1.50 meters. X, we don't know, but again, that's what we're looking for. We're looking for x. Y, again, because it hits the ground, the final height will be 0. V naught x, what is the initial velocity of the ball in the x direction? Ah, well, that's the x component of the velocity. Let me move the problem and give us a little more room so that we can work on this. To find Vx naught, or V naught x and V naught y, we know that the initial velocity, V naught, is 20 meters per second at an angle of 30 degrees. Well, V naught x and V naught y are the x and y component of the initial velocity. So V naught x would be this side of the triangle, V naught y would be this side. So we have that V naught x is the initial velocity cosine of the angle, so 20 meters per second cosine 30, which is 17.3 meters per second. And that V naught y will be the 20 meters per second sine of 30. So 20 sine 30, multiplying that out, 10 meters per second. So we put that in for V naught x, V naught y. Do we know the final velocities, Vx, Vy? No. But again, we know Ax, there's no horizontal acceleration, and Ay, again, negative 9.80 meters per second squared. Great. Let's get the equations and see if we can solve this. So what we want is x, and looking at the x equations, there is no x in the first equation. There is an x in the second equation, but we don't know t. There is an x in the third equation, but again, we don't know t. We might think, once again, that we could use the fourth equation to find x, but again, we know that a sub x is 0, and that's going to make this whole term equal to 0, and so we can't find x that way. So what are we going to do? Well, as usual, and again, there's no x's in the y component. This is a very standard approach. We saw it in the last problem. We're going to solve for t using the y motion. Is there any way we can solve for t in the y motion? Well, look through it. What do you think? Yeah, it turns out, whoops, sorry, I'm pointing at the second one. I meant the third one. We're going to use the third y equation to solve for t, and then we'll go back to the x equations and put t in and solve for x that way. Okay, let's give it a try. Starting out with the third y equation, we have y equals y naught plus v naught yt plus 1/2 ayt squared. Putting in the values, we have 0 equals 1.50 meters plus 10.0 meters per second t plus 1/2 times negative 9.80 meters per second squared, t squared. Again, I've got this negative term here leading the t squared, the a term in the, not the acceleration term, but I mean the a term in the ax squared plus bx plus c equals 0. And I like that to be positive, so I'm going to take everything to the other side, leaving us with 4.90 meters per second squared, t squared, minus 10.0 meters per second t minus 1.50 meters equals 0. Solving the quadratic, we have the opposite of b, negative 10, negative of that, 10.0 meters per second over 2 times a, 4.90 meters per second squared. This is basically why I like to keep that, that first a term positive, so I don't have these extraneous negative signs in the denominator that I'm likely to forget about. So we've got a positive denominator and then plus or minus the square root of b squared. Now b is negative, but a negative squared is the same as a positive squared, so I just drop that negative here. 10.0 meters per second squared minus 4a, 4.9 times c, which is negative 1.50, but we notice we've got a negative and a negative, so they will cancel out. All over 2a, 2 times 4.90 meters per second squared. Multiplying this part out, we have 1.02 seconds. Check the units, make sure that you get seconds for that. Plus or minus the square root, this whole thing, 1.16 seconds. Again, units finally end up as seconds. Make sure that's what you get here. Taking the positive sign, we get 2.18 seconds. Taking the negative, the minus, negative 0.14 seconds. Let's take a look at these two times and see if they make sense. First of all, we get a small negative time and a larger positive time. Going back to the picture, where would those times be where these conditions are satisfied? They would be back here. The a y value of 0 back before it was actually thrown, and then a y value of 0 over here after it's thrown. And we notice that the time after it's thrown is going to be a much larger time than the time before it was thrown. So getting a small negative time and a larger positive time makes complete sense. Which one do we want? We want the positive time. We want the 2.18 seconds. Sticking that into our third equation for x. The fact is that we could use the second equation for x if we remembered, well, because ax is 0, that Vx is equal to V dot x, and so this is also going to be 17.3, and then you could use the second equation in x. I just typically like to use the third equation. So we've got x equals x naught plus V dot xt plus 1/2 ax t squared. We know x naught is 0, we know ax is 0, so all we're left with is x equals V naught x 17.3 meters per second times t, 2.18 seconds, or x equals 37.7 meters. And the question about whether that goes farther than when the ball was thrown horizontally, yes, it does go farther, and that makes sense. When we had it thrown horizontally in a very similarly arranged problem, it went 11.1 meters, but if we throw it up at an angle of 30 degrees, it's going to go much further, and it turns out 37.7 meters. Great. All right, let's take a look at another problem.